Okay, let's see if we can wrap up this podcast series on advancing weather and climate forecasts with this podcast. So we looked at various issues thus far. We'll look at some more in terms of, let's see, let me get up this. So now you know big data and AI/ML are a big thing, and there is a lot of funding coming into weather and climate forecasts where existing numerical forecasts are converted to usable products with AI/ML, but also using AI/ML and data to improve the models themselves or improve parameterizations and so on. So potential major breakthroughs from ML. The use of ML will lead to significant progress over the whole range of classical modeling, data assimilation, and post-processing algorithms in the coming decade. It can be applied at each step of the weather forecasting process. Examples of topics relevant to NEWP can be found in this ECMWF report, European Space Agency and ECMWF workshop report. Machine learning for Earth system observations and predictions are also considered in that report. That's the title. Current and future research topics and potential advantages of utilizing ML include the following. Improve the utilization of observing systems, allowing forward planning of maintenance activities, and improved quality control as well as intelligent filling of data gaps. This is very critical. Advance the ability to input information from complex observing systems into models, data assimilation by providing better compression rates which will significantly increase the precision and speed of forward operators. Those are technical terms as steps in the data assimilation that I will not go into here, but I have discussed it elsewhere. Help better estimate model and observation errors in data assimilation through combining hybrid ML and data assimilation techniques. Allow incorporation of further complex subgrid physical parameterizations or training subgrid parameterizations on data provided by higher resolution models like large eddy simulation models. Subgrid scale processes are those that are not explicitly represented but are important, like mixing within a grid or fronts within a grid and so on. So AI can definitely help there. Large eddy simulations are another technique that technical term as well, that if you don't know, don't worry about it. Advanced post-processing of numerical variables by allowing incorporation of nonlinear correlations. So it's mixing AI techniques into post-processing the forecasts. Estimate impacts by combining ML model output and further observations or statistically relevant data. So models will have an intrinsic resolution of, let's say, even a case scale model with 1 kilometer resolution. But if you imagine a heat wave or a flood or a front of some sort, even within a city, neighborhoods will be differently affected. So then you might use AI with the forecasts to bring it down to that decision scale. Advanced nowcasting and improve rainfall estimation by applying ML to radar observations. So models have great difficulty in doing rainfall correctly, as we said. This is the context for convection permitting and explicit convection models as well. Use ML approaches to detect and forecast severe weather such as tornadoes, large hail, and damaging winds. Detect regimes where forecast failures are more likely to occur by combining ML with observations and model initial conditions and forecast output. Explore whether ML is a computationally efficient tool to replace the NWP forecast approach. There are approaches now funded by Schmidt Future to see if climate models can be built entirely on AI/ML. Well, we have to wait and see. Wide range of open source AI/ML frameworks. ChatGPT is getting a lot of attention, but there are other things relevant for us like TensorFlow and PyTorch, together with well-known programming languages like Python or C++, can support the development of these applications. Therefore, it becomes possible to tackle large-scale problems with the advent of dedicated accelerators. Cloud infrastructures provide easy access to accelerator hardware. If meteorological data are readily available, small and medium-sized enterprises can develop successful applications, especially if they bring together expertise from different disciplines. Earth system science is basically a very multidisciplinary problem anyways. Going towards recommendations toward improved systems for forecasting, investment strategies, of course. Improved forecast and better utilization of forecast information will require investments in the global observing system, which is very critical, often international, but some countries cannot afford to contribute, especially for sparsely populated parts of the world and oceans where the boundary layer and lower troposphere are often poorly sampled, and that affects the initialization and forecasts. Public investments in an accessible observational network will benefit all enterprise stakeholders, including the private sector and academia. Investments will also be needed in the supercomputing capability that is necessary to create weather and climate information of high accuracy, resolution, and reliability to address growing societal needs. These investment strategies must recognize the critical role of private sector in creating the instrumentation for observational networks and computational infrastructure. There are ideas floating around about having a world center where all countries are participating to do things like case scale modeling and then further post-processing and delivery of weather and climate services, but we have a long way to go there. This kind of global action, as we learned from the pandemic or climate actions, is not always easy. Hence, these investments should be accompanied by collaborations between the weather and climate enterprise, computer scientists, and industry on what changes need to be undertaken in the design of supercomputers, ML, and data sharing. Investments in observational networks should be coordinated with NEWP system development, for example, determination of the likely forecast improvement from a proposed observing strategy, timely development of data assimilation systems to significantly and efficiently improve forecasts and maximize the impact of observations on forecast skill. What is next? Changing roles. So as climate is changing and demands for information are changing, public, private sector and academic collaborations are changing. There is a changing role for WMO as a whole as well. There will be some notable shifts in roles, functions, and performance requirements for the NEWP enterprise stemming from the expected breakthroughs in technology and research developments. The development improvement of climate models would benefit from coordination with efforts to advance weather prediction with global weather models evolving in the years to come to explicitly represent convection. This keeps coming up because rainfall is one of the critical variables that we still don't have a very good handle on in terms of forecasts, especially at smaller scales. R&D efforts to overcome fundamental limitations in physical parameterization are accelerating and would benefit from collaboration between the weather and climate communities. Efforts to develop a unified single model across a range of timescales from nowcasting to centennial and spatial scales from convective scale to climate system Earth modeling should be accelerated, since such systems are possible, desirable, and perhaps even necessary for accelerating forecast advancements. The ECMWF model of international cooperation may need to be expanded and replicated to a certain extent to other regions, which will allow consolidation of human resources and expertise and optimization of running costs. ECMWF was a European Union thing, and UK has bailed out of it, so ECMWF sits in the UK still. There are, I think, plans to move it to Italy and so on. So you can see how geopolitics becomes part of organizing such efforts as well. Such a regional approach could be successful only with strong political support for national-based regional institutions and scientists to build capacity and consideration of existing regional climate centers. This approach is a task and challenge for WMO in cooperation with other relevant international organizations, including development agencies, private-public engagements, including development agencies, full stop. Private-public engagement could be a guiding principle to ensure partnerships, availability, and usability of skilled regional and local products. The challenges of big data then. Numerous segments of society are facing challenges in transporting, storing, and utilizing large data sets, and NEWP is at the forefront of this big data challenge. The scope of this challenge is evident in several papers which noted that 10 to the 7 observations are incorporated each day into operational weather prediction systems that produce 10 terabytes of model output per day. Increases in observation datasets like crowdsourcing advanced satellite observations, the movement of NEWP systems to ensembles operating at high resolutions of 1 to 3 kilometers, and attempts to observe and predict more components of the Earth system will only increase the difficulty humans and our technology face in handling these datasets. This big data challenge will pose a key dilemma for the NWEP enterprise and for society. High-resolution global ensemble modeling systems will continue to be run operationally, but only by those organizations having access to very significant supercomputing capabilities. This rules out many of the small countries and poor countries, for example. Currently, many NMHSs and private sector entities are operating their own regional modeling systems. National Meteorological Hydrological Services, I suspect. The quality and small-scale details of these new global models will likely exceed locally run models operating with limited computational resources. Thus, local models may appear to be a waste without adding value to freely available high-resolution global models. So the philosophy of how to do regional local downscaling when you have a case-scale global model has to be thought of carefully, and also a new paradigm can evolve where instead of multiple centers running multiple models at multiple resolutions with multiple configurations, can the global community run one large ensemble case scale 1 kilometer scale model, and then AI and ML and data etc. can be used to do regional and local scale climate services and weather services. Progressing together with low-income nations is a very critical thing because as we saw with the maps of weather hazards and loss events, everybody is in this now. Rich countries are also suffering. The importance of quality observations to global prediction means that stabilizing the national observing networks in low-income countries and ensuring their long-term maintenance to provide standard quality observational data are of paramount importance. One striking element of addressing this situation is that the massive investments, estimated as billions of dollars, through various development assistance projects engaging numerous development funding agencies, have often provided disappointingly low impacts on local capacity. So we're talking about the losses being at billions of dollars each year and investing a smaller amount of that into building these prediction systems and observational systems to go with it, and the human capacity, workforce, etc. So how do we weigh the return on investment? Some analysts pointed out that the main reason for such a failure is that the development funds were spent mostly on equipment such as automatic weather stations, communication systems, computers to run NEWP, and weather radars, widely not utilized after delivery to the maintenance problems due to maintenance problems. So systems are set up, but maintenance problems, for example, the observational buoy Rama in the Indian Ocean has basically been dysfunctional since COVID because of lack of maintenance. So how do we deal with this? Unfortunately, less attention is often given to the longer-term success of these investments, which requires planning and funding to maintain and sustain instrumentation, improve communication systems and service delivery, capacity building including training and retaining staff, access to and utilization of observations and forecast products from the WMO and major operational centers, engagement with the private and academic sectors, and advanced data management systems. There are some relevant papers here that you should look up. Finally, coming to the conclusions, I will read the whole thing just to make sure I re-emphasize the points. The decade of 2021 to 30 will be the decisive period for realization of the 17 United Nations Sustainable Development Goals and targets outlined in the Sendai framework. This is a framework on dealing with hazards. Most of these disaster management, recovery, etc. Most of these goals have links with the changing environment, climate change, water resources, and high-impact weather and environmental events. The desired outcomes in all areas require enhanced resilience, which is also the main call of the WMO Vision 2030. The advances expected in weather forecasting and climate prediction during this decade will support those ambitious goals by enabling a next generation of weather and climate services that help people, businesses, and governments to better mitigate risks, reduce losses, and materialize opportunities from the new intelligence of highly accurate and reliable forecasts. This is a promise and a potential that must be reached in this decade. And mapping everything onto the sustainable development goals in terms of access to water, energy, health, education, etc. become very critical. Okay, these advances will also help assess systemic risks arising from the long-term evolution of weather and climate high-impact events, variability and change across time and space. This paper has shown the major challenges of and opportunities in each of the first three components of the innovation cycle: infrastructure, R&D, and operation. Several key factors will determine the success and effectiveness of future progress in NEWP, including the open data access, ability for near real-time data processing and transmission, monitoring data and forecast quality, quick and focused dissemination to users, and advances in societal decision making. So decision making has to trust the forecasts and develop its own sense of the uncertainties, like the way weather forecasts are used by people in the northern hemisphere, because they watch it day in, day out, several times a day, make decisions based on those. This comes from dealing with the information over time and knowing that they are useful but come with some uncertainties. Some of these factors are common to the three components of the innovation cycle: infrastructure, R&D, and operations, but their implication and logic can be different, such as sharing data policies or high-performance computing requirements for R&D and operation. It has been emphasized that the only way to address these challenges and enable the uptake of the technological and scientific achievements is through inclusive public, private, and academic partnerships. The academic role has to get bigger and bigger in working on actual problems, translating science or process understanding into predictive understanding and improving predictions. And of course, bringing AI ML techniques to translate the skillful forecasts into scales at which decisions are made sectorally, whether it's food, water, energy, health, transportation, buildings, infrastructure, and so on. Okay, so this is the end of this three podcasts, but each one is important. But hopefully you can also read the paper or the original WMO report on this advancing weather and climate forecasting to get your own sense of where your interest lies and what the relevant papers are, because the report comes with a long list of excellent papers on the topics as well. Okay.